Today we're going to finish out Chapter 4, Elementary Number Theories and Methods of Proof. Indirect argument and two famous theorems. When mathematics flourished at the time of the ancient Greeks, mathematicians believed that given any two line segments, say A and B, a certain unit of length could be found so that segment A was exactly m units long and segment B was exactly n units long for some integers m and n. The segments are said to be commensurable with respect to the special unit of length. Then the ratio of the lengths of A and B would be in the same proportion as the ratio of the integers m and n. Now, it is easy to find a line segment of square root of 2. Just take the length of the diagonal of a unit square by the Pythagorean theorem. C here, it would be the square root of 2. If the belief of the ancient Greeks were correct, there would be integers m and n such that the length of the diagonal and divided by the length of the side would equal to some integers m and n. And this would imply that square root of 2 would be a rational number. But we know it's not. And square root of 2 is irrational. Proved by contradiction that 1 plus 3 times the square root of 2 is rational. Well, the essence of the argument is the observation that if 1 plus 3 times the square root of 2 could be written as a ratio of integers, then so could square root of 2. But by theorem 481, we know that to be impossible. So 1 plus 3 times the square root of 2 is irrational. Are there infinitely many prime numbers? You know that a prime number is a positive integer that cannot be factored as a product of two smaller positive integers. Is the set of all such numbers infinite, or is there a largest prime number? The answer was known to Euclid, and a proof that the set of all prime numbers is infinite. Euclid's proof requires one additional fact that we have not yet established. If a prime number divides an integer, then it does not divide the next consecutive integer. They don't, however, go into Euclid's proof. But for any integer a and any prime number p, if p divides a, then p does not divide a plus 1. And theorem 484, the set of prime numbers is infinite. They discuss that, but they don't prove it. That seems kind of a letdown. Missing some important information there. When to use indirect proof. The example in this section, we have not provided a definitive answer to the question of when to use direct or indirect proofs. Many theorems can be proved either way. Usually, when both types of proof are possible, indirect proof is clumsier than the direct proof method. In the absence of obvious clues suggesting indirect argument, first try to prove the statement directly. Then, if that does not succeed, look for a counterexample. If the search for a counterexample is unsuccessful, look for a proof by contradiction or contraposition. And that is it for this slide deck. And let's see if this behaves. The handshake theorem. An application of what we've been covering so far. The total degree of a graph is the sum of the degrees of all the vertices of the graph. So the total degree of this graph here is the sum of all the degrees of the individual vertices, which are 1, 4, 2, and 3, which totals 10. So the total degree of the graph shown is 10. So the handshake theorem. If G is any graph, then the sum of the degrees of all the vertices equals twice the number of edges of G. Specifically, if the vertices of G are B1, B2, etc. to Bn, where n is a non-negative integer, then the total degree of G is the degree of V1 plus the degree of V2 plus the degree of whatever, all the way up to the degree of Vn, which equals 2 times the number of edges of G. After all, the edges have to have 2 endpoints, so that's 2 points of degree that you have for each edge. So because of that, it's 2 times the number of edges. 2 times any integer is even, so the total degree of a graph is going to be even. Draw a graph with specified properties or show that no such a graph exists. A graph with 4 vertices of degree 1, 1, 2, and 3. Can that graph be shown? No, it can't, because the degree would be odd. The degree has to be even. Has to be an even number. A graph with 4 vertices of degree 1, 1, 3, and 3 is possible, however, because that is an even number. It can be drawn in a lot of different ways, as shown here. A lot of different ways. Just as an example. In any graph, there is an even number of vertices of odd degree. So is there a graph with 10 vertices of degree 1, 1, 2, 2, 2, 3, 4, 4, and 6? An odd number of odd degrees indicates an odd number of vertices overall, and an odd number of degree overall, which makes it impossible. So no such graph would be possible because it would have 3 vertices of odd degree. Note that this is the same result could have been deduced directly from corollary 492 by computing the total degree, which would be 29, and noting that it is odd. However, proposition 493 gives the result without needing to perform this addition. Now, applying this. At a meeting attended by a group of 4 people, 4 people shook hands with 1 other person. 6 people shook hands with 2 other people. 2 people shook hands with 3 other people. And the rest shook hands with 4 other people. No 2 people shook hands with each other more than once, and a total of 23 handshakes occurred. How many people attended the meeting? A little complicated, but it's calculatable. Define a graph G by letting each vertex represent a person. and letting each edge represent one handshake between two people. Let X be the number of people who shook hands with 4 or other people. Then the total degree of the graph would be 4 times 1 plus 6 times 2 plus 2 times 3 plus X times 4, or 22 plus 4X. Because 4 people shook hands with 1 person, etc. And X people shook hands with 4 people. So, in addition, since a total of 23 handshakes occurred, the graph has 23 edges. And the total degree is twice the number of edges, so the total degree would be 46. So it follows that 22 plus 4x equals 46, 4x equals 24, and x would equal to 6. So 6 people at the meeting shook hands with 4 other people. Now the total number of people at the meeting is the sum of the number who shook hands with 1 other person, 2 other people, 3 other people, and with 4 other people. Therefore, the total number of people at the meeting equals 18. Special graphs. A simple graph is a graph that does not have any loops or parallel edges. In a simple graph, an edge with an endpoints v and w is denoted by the set roster notation curly brace vw curly brace. Draw all the simple graphs with 4 vertices, u, v, w, x, and 2 edges, one of which is u, v. Well, there's 5 ways of doing it. They show them all here. So, simple graphs, no loops, no parallel edges. Let n be a positive integer. A complete graph on n vertices is a simple graph with n vertices and exactly 1 edge connecting each pair of distinct vertices. So, all the vertices are connected to each other by 1 edge. As shown with the first 6 here, or first 5 here. Okay, 1 through 5. Prove that for any positive integer n, a complete graph on n vertices has n times n minus 1 all over 2 edges. Well, suppose n is a positive integer and kn is a complete graph on n vertices. Because each vertex of k of n is connected by exactly 1 edge to each of the other n minus 1 vertices, the degree of each vertex of the graph is n minus 1. And the total degree of the graph is the number of vertices of the graph times the degree of each vertex of the graph, which is n times n minus 1. By the handshake theorem, the total degree of the graph equals twice the number of its edges. So since the total degree is n times n minus 1, n times n minus 1 equals 2 times the number of edges of k of the graph. Dividing by 2 gives that the number of edges of the graph is n times n over 1 all over 2. Definition. Let m and n be positive integers. A complete bipartite graph on m and n, an ordered pair here, denoted by k of m and n, is a simple graph whose vertices are divided into 2 distinct subsets, V with M vertices and W with N vertices in such a way that every vertex belongs to one of V or W, but no vertex belongs to both. And there is exactly one edge from each vertex of V to each vertex on W. There's no edge from one vertex of V to another vertex of V, and there's no edge from any one vertex of W to any other vertex of W. The words don't really capture what's being said here very well. Images do. So you have two groups of vertices, and they're fully connected between the two. But no vertex of V is connected to another vertex of V, and no vertex of W is connected to another vertex of W. Otherwise, it is a fully connected graph. One place where this type of graph is used is in neural networks. Layers of nodes, are connected in a bipartite type of situation. Each layer is connected to the next layer by a complete bipartite graph. So that is one application of the complete bipartite graph. And that is it for that one. And finally, we got a glitch. Try this again. Elementary number theory, final section, algorithms. Now, I really don't like this section. It's wordy and doesn't show a whole lot. Word algorithm refers to a step-by-step method for performing some action. We all know this from CS1. That's what an algorithm is, right? Step-by-step process. Some examples of algorithms are food preparation, assembling kits, sewing pattern instructions, that sort of thing. Part of elementary school math was devoted to learning algorithms for doing arithmetic, such as multi-digit addition, subtraction, multiplication, and division. An algorithmic language. Now, see, this is one of the reasons why I don't like this particular thing. The algorithm language used in this book is kind of a pseudocode, combining elements of Python, C, C++, and Java. But when we get into the pseudocode that they use, it uses Pascal and BASIC, not Python, C++, C, or Java. It uses symbology and keywords from the languages Pascal and BASIC. So it's just like misleading. It's like that Python, C++, C, Java, you're not going to see that in this. All right, in high-level computer languages, the term variable is used to refer to a specific storage location in a computer's memory. So variable X, memory location corresponding to X contains, for example, the value 3. Any given storage location can only hold one value at a time. So if a variable is given a new value during program execution, then the old value is erased. The data type of a variable indicates the set in which the variable takes its values, whether the set of integers, real numbers, character strings, or Boolean variables or values, whatever. See this colon equals? That's from Pascal. That's an assignment, as opposed to comparing whether or not the two values are equal. It's assignment. And in this case, that means x is assigned the value of e. And when an assignment statement is executed, this is about the order of operations here. The assignment to the variable x in the previous example is the last in order of operation. The entire expression e is evaluated first, and then its value is placed in the memory location corresponding to x. Ordinarily, algorithm statements are executed one after another in the order in which they are written. Conditional statements allow this natural order to be overridden by using the current value of program variables to determine which algorithm statements will be executed next. And so here's an example of BASIC. It uses the if, then, else structure. You don't see that in Python, C++, or Java. But you get the general gist of what this structure is. Condition is a predicate involving algorithm variables, and S1 and S2 are algorithm statements or groups of statements. We generally use indentation to indicate statements belong together as a unit. Now that does come from using the indentation, coming together, grouping things as a unit. That does come from Python. That's how you designate what goes after in an if statement or a for loop. When ambiguity is possible, however, we may explicitly bind a group of statements together into a unit by preceding the group with the word do and following it with the words end do. Now, if they were using C++ or Java, it would be curly braces to indicate a group. But the execution of the if-then statement, if-then-else statement, occurs as condition is evaluated for the truth or falsity of the resulting statement. The condition is true, then S1 is executed, and execution moves to the next algorithm statement following the if-then-else statement. If condition is false, then S2 is executed, and execution moves to the next algorithm statement following the if-then-else statement. So let's look at A. If x greater than 2, then y equals x plus 1, else x equals x minus 1, and y equals 3x. What is the value of y after executing these segments this segment for the following values of x? X equals 5. If x is greater than 2, which it is, then you would say y equals x plus 1. So it would be 6. Now if x equals 2, x greater than 2 is false, so it would be x equals x minus 1, making it 1, making x 1, and then y equals 3x it would be 3 times 1, y would equal to 3. just tracing through a program like you would in C++. So yeah, y equals 6 and y would equal to 3. A while loop has this form. While condition is true, execute the statements that make up the body of this loop, and end while. I'm not sure where end while comes from. In BASIC, it might come from Pascal. BASIC, it was wend, while end, combined into one word. But it was while wend. But I've never seen end while in Python, C++, or Java. Yeah, the word while marks the beginning of the loop, and the end while marks its end. And you all know how a while loop works, right? Checks the condition. If it's true, run the statements in the loop, go back to the beginning of the loop, check the condition again. If it's false, jump out of the loop and continue afterwards. Yeah. Pretty basic stuff, basic programming. So trace that. Given I is an initial value of 1, and it goes through the process of calculating S and I. And S and I end up equaling to 3 because they have what's called a trace table. You trace the iterations of the loop and the value of each variable at each iteration. Helpful to be able to know how to do that. You just trace through, do the variables, adjust the variables with each iteration, and you can probably tell if there's you can determine whether or not it would end up being an infinite loop versus a terminating loop, that sort of thing. But yeah, you do a trace table that way. Now the for next loop for a variable initial expression to final expression, statements that make up the loop, and then next variable, again from BASIC, not from the for they mentioned earlier. And it has a loop variable that equal to the value of the initial expression. A check is made to determine whether the value of the variable is less than or equal to the value of the final expression. If the value of the variable is less than or equal to the value of the final expression, then the statements in the body of the loop are executed in order. The variable is increased by 1 and execution returns back to step 2. If the value of the variable is greater than the value of the final expression, then execution passes to the next algorithm statement following the loop. So it doesn't do a trace table for a for next loop. It wants you to convert it to a while loop and then construct the trace table. So why you'd want to do that, I'm not sure, but the value of x would be 1, 4, 9, and 16 at each iteration of the loop. I squared, x equals I squared. It's not cumulative. It's just changes the value of x each time. So that's converted from the for loop to the while loop, and I think the for loop's neater. It's fewer lines of code. This is 5 versus 3 lines of code because you have to initialize separately in the while loop, and you have to do a separate increment of I at the end of the while loop. Trace note table would be 1, 2, 1, 4, 9, 16. So notation for algorithms. We will express algorithms as subroutines that can be called upon by other algorithms as needed and used to transform a set of input variables with given values into a set of output variables with specific values. The output variables and their values are assumed to be returned to the calling algorithm. For example, the division algorithm specifies a procedure for taking any two positive integers as input and producing the quotient remainder of the division of one number by the other as output. Whenever we call whenever an algorithm requires such a computation, the algorithm can just call the division algorithm to do the job, like calling a function in C++. Same thing. The only difference is really in the book, in math in general, you can return two values from two or any number of values from an algorithm call like this. In C++, you can only return one value or one object from a function. So to describe an algorithm, you get the name of the algorithm together with a list of input and output variables like the data type and arguments for the parameters for the function that you're calling or you're defining in C++. A brief description of how the algorithm works. The input variable names labeled by data type, whether integer, real, or number, or integer, real number, or whatever. The statements that make up the body of the algorithm, possibly with explanatory note comments, and the output variable names labeled by data type. So the output is just one data type in C++. That's declared in the first line of a function definition. The division algorithm. For an integer a and a positive integer d, the quotient remainder theorem guarantees the existence of integers q and r such that a equals dq plus r, and r is greater than or equal to 0 but less than d. So the division algorithm shown here, basically you start out r as being equal to a, while r is greater than or equal to d, subtract d from r and increase the quotient by 1 until the quotient until r is less than d, at which point the q and r are valid results of the algorithm. So trace the action of the algorithm on the input variables a equals 19 and d equals 4. Well, r equals a to begin with, d equals 4, so you subtract 4 each time until r is less than d, which is 4. Q is equal to 4, and the quotient equals 4, and the remainder equals 3 at that point. So, simple way of doing division. Repeated subtraction. The Euclidean algorithm. The greatest common divisor of two integers, a and b, is the largest integer that divides both a and b. For example, the greatest common divisor of 12 and 30 is 6. The Euclidean algorithm provides a very efficient way to compute the greatest common divisor of two integers. It is let's see here. Definition here. Let a and b be integers but that are not both 0. Greatest common divisor of a and b is denoted by GCD a and b of a and b. Is that integer d with the following properties. D is a common divisor of both a and b. In other words, for every integer c, if c is a common divisor of both a and b, then c is less than or equal to d. So, what's the GCD of 72 and 63? What's 72 a product of? 9 and 8. Okay, what's the product of, what's 63 the product of? 7 and 9. So what do they have in common? 9. There you go. In the definition of greatest common divisor, GCD 00 is not allowed. Why not? Well, yeah, so number 9 here. And for the C, suppose GCD 00 were defined to be the largest common factor that divides 0 and 0. Problem is that every positive integer divides 0, and there is no largest integer. So there is no largest common divisor. So there you go. Now, if r is a positive integer, then greatest common divisor of 0 and 0, r and 0 is going to be r. If a and b are any integers, but not both 0, then, and if q and r are any integers such that a equals bq plus r, then GCD a and b equals GCD of b and r. That's the Euclidean algorithm, the basis for the Euclidean algorithm. So you got the Euclidean algorithm here, where you have a is greater than b, b is greater than or equal to 0. Find the greatest common divisor of a and b. First check if b equals 0. If it is, then GCD AB equals a. If it isn't, then b is greater than 0, and the quotient remainder theorem can be used to divide a and b to obtain a quotient and a remainder. So GCD of a and b equals the GCD of b and r. Thus, the problem of finding the greatest common divisor of a and b is reduced to the problem of finding the greatest common divisor of b and r. Now just repeat the process starting at 2, but use b instead of a and r instead of b. The repetitions are guaranteed to terminate eventually with r equals 0, because each new remainder is less than the preceding one, and all are non-negative. So you use the Euclidean algorithm to find the greatest common divisor of 330 and 156. So you divide 330 by 156, take the remainder is 18, and then take 156, GCD of 156 and 18, and repeat the process. Divide 156 by 18, you get a remainder of 12. So you have 18, greatest common divisor of 18 and 12, which equals the greatest common divisor, greatest common divisor of 12 and 6, because 18 divided by 12 is has a remainder of 6. And one more time, 12 divided by 6 is 2 with a remainder of 0. So putting all the equations together, each greatest common divisor is reduced down to greatest common divisor of 6 and 0, which by definition is 6. If r is a positive integer, then greatest common divisor of r and 0 is r. Therefore, the greatest common divisor of 330 and 156 is equal to 6. So there you go. Here's the pseudocode version of the Euclidean algorithm, written for using formal algorithm notation. You can peruse this on the files, in the slides on the files. I already went through the algorithm once. No need to go through that all again. But I believe, it wants to do a trace table for the algorithm. Same numbers, and you see the trace A and B, A, B, and R, and the greatest common divisor being 6. And that is it for the slide deck, and that is it for chapter 4. Keep in mind there is the midterm on Thursday. Open notes as usual. I believe it's a comprehensive, so all 4 chapters will be covered. So bring all your notes, not just chapter 4. Also keep in mind that the homework for chapter 4 is due before the class begins on Thursday. So don't delay on that. Anyway, I guess that'll be it for the day. Have a good day. See you on Thursday.